The universe expanded by a factor of 10 to the power of 26, in a sliver of time so small it defies comprehension. Today's entire observable cosmos, spanning 93 billion light-years, was once smaller than a single cell. So, what exactly happened in that unimaginable instant? Pause for a moment and try to conceive of the universe's beginning as a state where the very notion of before loses all meaning. This is the primordial singularity, a point of infinite temperature and density where space and time themselves were born, a concept established by NASA's WMAP mission in 2010. In this unimaginable state, three of the four fundamental forces, electromagnetism, the weak force, and the strong force, were unified into a single superforce, with gravity standing alone, a situation described by CERN in 2023. The temperature at this moment, a mere 1043 seconds after the beginning, was an almost incomprehensible 10N32 Kelvin, a figure reported by The Guardian in 2015, a degree of heat so intense that matter as we know it could not exist. Now let's try to grasp the minuscule duration of this epoch, a length of time so short it defies intuition. We can measure this by considering the most precise clock ever built, the atomic clock at NIST, which would only lose 1 second in 30 billion years. Yet, the time we are discussing, the Planck time, is so incredibly brief that it is 10 to 32 times shorter than the smallest tick of that clock. To visualize this, imagine the fastest possible tick you can conceive, and then divide it into 10 trillion parts. This is the scale we are dealing with, a single moment so fleeting that it challenges the limits of our imagination. The modern physics we use to describe the universe breaks down completely at this point. The two great pillars of our understanding, general relativity and quantum mechanics, which govern the cosmos and the subatomic world respectively, are fundamentally incompatible under these extreme conditions, leaving a gap in our knowledge that physicists at Stanford have yet to fill, a frontier that remains a profound mystery. So we are left at the very threshold of existence, in a state that is completely alien to our everyday experience. The question of what happened in this first sliver of time points not to a physical process, but to the very nature of time itself. If time began here, what does it truly mean for it to begin? Is it a river that was always flowing, or did it simply switch on like a light in a dark room? The laws of physics, as we know them, offer no answer from within this realm, suggesting we may need to look beyond them for a description of this origin point. This is the mysterious and profound stage set for the explosive events that follow, the singular and elusive beginning of our universe. The clock's tick is a lie, a macroscopic convenience. Its smallest measurable increment is a coarse, lumbering beat compared to the quantum flailings of that first instant. To grasp the Planck time, one must abandon the familiar rhythm of seconds and minutes entirely, and instead attempt to divide that single, swift tick by a factor of 10 billion trillion. The result is so small that it defies the very grammar of scale, a number so far removed from our daily reality that it feels less like a measurement and more like a philosophical abstraction. This is not a duration you can feel, not a beat you can count. It is a static-sounding, unimaginably thin slice of change that defines the boundary of physical law itself. Within this brutal, inconceivable brevity, the universe was not a place of light or matter as we know it. Instead, it was a primordial, undifferentiated soup of pure energy, a roiling, seething ocean at a temperature of roughly 1032 Kelvin, a figure so immense that the very concepts of hot and cold lose their meaning. In this throbbing, formless pressure cooker, three of the four fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, were fused into a single unified superforce, a perfect symmetry that would forever shatter moments later, leaving gravity as the lone outcast, a weird, separate law already hinting at its future role in shaping the cosmos. There was no up, no down, no here, no there, only a hyper-dense searing point of everything, yet nothing in particular. This is the point where our models, from Newton to Einstein to the standard model of particle physics, silently but firmly raise a hand and say, "Stop." They cannot see beyond this curtain. The mathematics, so elegant and predictive in our macroscopic world, dissolves into a cacophony of meaningless infinities where it is impossible to tell cause from effect, or even if the sequence of events holds any sway at all. This is the stark, insurmountable wall between our universe of galaxies and nebulae and the absolute nothing from which it was born. Can we truly understand a state where the separation between particles, between forces, and even between events themselves is a meaningless concept, a blur without edge, a haze without form, a void that is nevertheless everything? Perhaps the only thing we can do at this precipice is to feel the ultimate weight of that question pressing down upon the very logic we use to ask it. We often talk about the Big Bang as a single massive explosion, but the very earliest moments were far stranger and more violent than that. Let's focus on the second scene of this cosmic film, the era of inflation, which began at 10:36 seconds. This is the story of the fastest, most dramatic expansion our universe will ever experience, driven by a theory proposed by a young physicist named Alan Guth in 1980. At MIT, Guth was wrestling with a problem. The universe we see today is remarkably uniform, but the standard model of the Big Bang couldn't explain why. His solution, which he published in 1981, was a radical idea that the universe underwent a period of hyperexpansion, inflating faster than the speed of light itself. The numbers involved are almost impossible to grasp. Over a staggeringly brief window from 10:36 to 10:32 seconds, the universe expanded by a factor of at least 1026. That's a 1 followed by 26 zeros, meaning the cosmos grew by a million trillion times in less time than it takes light to cross a single atom. To feel the scale of this, imagine a balloon. Now imagine that balloon inflating from the size of a pinhead to the size of a soccer ball, not over a few seconds, but in a single instantaneous flash. In that single moment, the fabric of space itself was stretched from a quantum speck to something that would become the seed of every galaxy we see today. How did this happen? The driving force was a strange kind of energy, often called the inflaton field. It wasn't a normal force like gravity. It was a repulsive energy that caused space itself to expand at an incredible rate. Think of it like a phase transition, similar to liquid water boiling into steam. Just as boiling water releases energy, the transition of this inflaton field released its stored energy. This process, known as reheating, is what filled the universe with the first matter and radiation. In an unimaginably fast period, the energy of empty space transformed into the particles that would eventually build stars, planets, and us. This rapid-fire expansion is fundamentally different from the slow, gradual expansion we see today, which is driven by dark energy. Inflation was not just a slightly faster version, it was a different phenomenon entirely. It was a brutal, violent stretching of space that lasted for a tiny fraction of a second. By the time this scene ends, at the 10:32 second mark, the universe is cold enough for the energy to convert into particles. The entire observable universe at this point is not a vast emptiness. It is a seething, expanding sphere with a diameter of just about 1 micron, a fraction of the width of a human hair. The stage is set. A period of intense expansion is over, and the universe is now cooling, preparing to build something new from its own energy. The universe at 1 micron is a concept that defies the very core of our intuition. Hold a single grain of salt on your fingertip. That minuscule speck is 1,000 times larger than the entire cosmos at this moment. Every proton, every neutron, every particle that would eventually compose the trillions of stars in the observable sky is crammed into a space smaller than a single living cell. Imagine the sheer pressure, the impossible density of matter and energy compressed to a point where the very fabric of reality is a searing, opaque plasma. There is no light in the way we know it, just a blinding, uniform roar of primordial energy. The emptiness we perceive today was, at this instant, an overwhelmingly hot and bright furnace, its temperature exceeding 10,000 billion degrees. This is the hand that dealt the cards for everything to come. How could a phased transition be so violent? The answer lies in the nature of the inflaton field itself. Picture a ball resting at the top of a perfectly flat, high plateau. That is the universe before inflation, balanced in a false vacuum. A quantum fluctuation nudges it. It begins to roll off the plateau. As it rolls, it does not gather speed gradually, but instead triggers a process akin to supercooling. It is like water that has been chilled below freezing without turning to ice, waiting for a single speck of dust to trigger a sudden, explosive crystallization. The entire process does not unfold like a slow rumble, but as a chain reaction sweeping across space at a terrifying pace. This is not a gentle release. It is the sudden, catastrophic decay of the inflaton field, dumping its colossal store of energy directly into the creation of a hot particle soup. The energy of reheating did not just create a few stray particles. It created a state of matter so hot and dense that the fundamental forces of nature themselves were unified. In this inferno, quarks and gluons roamed freely in a state known as quark-gluon plasma, unbound by the strong nuclear force that would later confine them. It is a zoo of exotic particles, many of which no longer exist in our universe except in powerful particle accelerators. These particles crashed into each other, annihilating in flashes of pure energy, only to create new pairs from that energy again. This chaotic dance of creation and destruction was the primary occupation of the cosmos. There were no atoms, no molecules, just the raw, undifferentiated ingredients waiting for the temperature to drop enough for the fundamental forces to crystallize into their distinct forms. This moment is the ultimate dividing line in cosmic history. Before it, the universe was a sterile, rapidly inflating void of energy. After it, the universe was filled with the very constituents of matter. The entire history of the cosmos, the formation of hydrogen and helium, the ignition of stars, the forging of heavy elements in supernovae, and the subsequent creation of planets and life, all stem from this one brief, violent event. It is the primordial Big Bang within the Big Bang. A comparison to a human scale might help. Imagine the entire population of Earth being compressed into the volume of a single apple. The resulting explosion would not be a gentle puff. It would be the most powerful force conceivable. That is the kind of energetic output we are describing here. When the inflaton field finally decayed, it did not leave a quiet vacuum. It left a dense, hot, and full universe. The giant, empty framework of space was now furnished with the raw material for reality. The particles created in this instant would spend the next 13.8 billion years drawing themselves into ever more complex structures. Imagine the entire universe, every particle that will ever exist, compressed into a soup so hot and dense that the very concepts of matter and light have no meaning. This is the quark-gluon plasma, a state that existed from 1012 to 10.6 seconds after the Big Bang. The energy density at this moment was roughly 10^98 joules per cubic meter, a figure so vast it dwarfs the 1033 joules per cubic meter found at the core of a neutron star by a factor of 1065. It wasn't just hot. It was a roiling, seething ocean of pure energy, a cosmic pressure cooker where the fundamental building blocks of our reality were free and unbound. Normal matter, the stuff of our world, simply could not exist in this inferno, as the very forces that hold atoms together were overwhelmed by the sheer violence of creation. But this fury was not eternal. As the universe expanded, it began to cool, and at the crucial moment of 10.6 seconds, the temperature dropped below a critical threshold, 1013 Kelvin. It was at this precise point that the universe underwent a transformation as significant as water becoming ice. The free-floating quarks, which had been zipping around independently, suddenly found themselves able to stick together. This was the beginning of the Hadron epoch, a period spanning from 10.6 seconds to a single second after the start. In this incredibly brief window, the first proton and neutron pairs were forged from the cooling chaos. Yet this was not a gentle, peaceful assembly. It was a frantic, chaotic time where these newly formed particles were constantly being created and just as quickly destroyed by collisions with other particles, a cosmic battlefield where existence was a fleeting, temporary state. The process that defined this chaos bears a remarkable resemblance to something we see every day. As the universe expanded and cooled through this phase transition, energy was released in a process much like steam condensing into water, a phenomenon known as reheating. This released energy, in turn, became the raw material for the creation of particles and radiation. To get a sense of this state, we can turn to the massive ALICE experiment at CERN. In 2023, scientists there recreated this primordial soup by slamming lead ions together at incredible energies. They found that this quark-gluon plasma, far from being a chaotic, formless gas, actually behaves like a perfect liquid, one with almost no viscosity at all. This discovery was a shock, challenging all the theoretical models that had been developed to predict its behavior and giving us a tangible glimpse into the very nature of that first second. This perfect liquid state provides the crucial context for the events that followed. As the universe continued its rapid expansion, the temperature dropped further, and the balance between the creation and destruction of these hadrons began to shift. The energy was no longer sufficient to constantly produce new proton-antitron pairs. This is where the asymmetry of the universe's building blocks became a life or death matter. For every 1 billion antimatter particles that were annihilated, a tiny excess of one matter particle survived, a fraction that would define the composition of everything we see today. The frantic collisions, however, meant that a stable atomic nucleus was still an impossibility. The universe was still too hot, a single second being far too early for the first elements like helium to form. That would have to wait for a few minutes of cooling. So, as the first second of existence drew to a close, the universe was a rapidly cooling, thinning haze of matter and radiation. Out of the chaos, a specific pattern was beginning to emerge from the wreckage of creation. A critical balance was being struck in this dynamic equilibrium of particle creation and annihilation, a cosmic tally that would determine the building blocks of all future matter. The one notable exception to this relentless process was the neutrino, which, with its almost negligible mass and lack of charge, could now escape the plasma and travel freely through the universe. This was a significant event as their escape would eventually create a faint cosmic background radiation, an echo of this very moment. For the hadrons that remained trapped in the searing flow, however, a crucial ratio was being determined, a number that would dictate the chemical composition of the cosmos. The ratio of protons to neutrons, a final, defining legacy of this monstrous first second. The universe has just passed through the chaos of the quark-gluon plasma, and now, between 10 to the minus 6 seconds and the 1 second mark, it enters the hadron epoch, a brutal, relentless contest of creation and annihilation. At this point, a single proton forms, only to be smashed apart by a passing meson almost immediately, its constituent quarks scattering back into the seething soup. This is a cosmic demolition derby where the only currency is mass energy, and the speed of the exchange is staggering. The question that hangs over this crucible is simple. Amidst this constant destruction, which particles will ultimately survive to build the universe we know? The answer comes down to a tiny, almost imperceptible difference in weight. Protons and neutrons are being forged in this fire, but they are not created equal, as physicists at CERN have noted in their 2023 analyses. A proton is ever so slightly lighter than a neutron, by about 0.1% of its total mass. This means it takes slightly more energy to build a neutron out of quarks than it does to build a proton. So in the frantic push and pull of the first second, the universe, still cooling from its unimaginable peak, favors the proton. The result is a specific ratio. For every 7 protons created, only 1 neutron is made, a 7:1 ratio locked in by the laws of physics themselves. This isn't just a fun fact, it's the blueprint for all future chemistry. If the ratio had been 1:1, the early universe would have been a very different place, leaving no leftover hydrogen to fuel the stars for billions of years. The hadron epoch is a non-stop frenzy, where the creation and destruction of these heavy particles is the only rule, and the potential for atomic nuclei to form is an impossible dream. The heat is simply too intense, the particles are moving too fast, and any brief clumsy union is ripped apart in a fraction of a nanosecond. The first atomic nucleus, the first bit of stable matter, is still 3 minutes away, a lifetime compared to the drama of this single second. Here's something incredible. While we can't look back at this moment directly, we are surrounded by its ghost. As the universe cools to a critical threshold during this epoch, a subtle change occurs. The neutrinos, ghostly particles that barely interact with anything, stop being entangled with the plasma and finally break free, streaming out into the cosmos as unencumbered as I am breaking this sentence. This flood of particles forms the cosmic neutrino background, as described in research from 2020, a faint echo of the universe that existed before atoms, before stars, before the light we can see. To understand how we know about these ancient signals, picture the COBE satellite, launched by NASA in 1989. Over 3 years, scientists at the Goddard Space Flight Center analyzed its data, finding the cosmic microwave background radiation to perfectly match the spectrum of a black body. This discovery, which earned John Mather and George Smoot the 2006 Nobel Prize in Physics, proved that the universe has a memory, a record of its early state. These background signals, whether from light or neutrinos, are the fossilized whispers of the violence of that first second. By the end of that first second, the hadron epoch is drawing to a close. The incredible heat that defined the early universe, at billions of degrees, is now a fraction of what it was, but still far too hot for any organized structures. The stage is set, the actors, the protons and neutrons are in place, and the ratio is locked. But the question lingers in the slowly expanding darkness, hanging over the seething matter. What will happen to all these protons and neutrons now that the universe has cooled just enough to let them exist? The answer is not a story of formation, but of a coming catastrophe, where matter itself meets its own mirror image and fights for survival. The stage for our existence was set by a cosmic game of musical chairs, one where the music stopped for almost every particle. In that first second, matter and antimatter were locked in a deadly embrace, each pair destined to annihilate the other in a flash of pure energy. The physics seemed brutally simple, equal and opposite, a perfect symmetry that would leave the universe as nothing but radiation. But here is the scandal at the heart of our reality, a fact so strange it feels like a miracle. The asymmetry between matter and antimatter, a concept known as baryon asymmetry, is not perfect. For every 1 billion pairs of quarks and antiquarks that met and vanished, a single quark was left behind. 1 out of a billion, a cosmic lottery with odds so steep they are nearly impossible to grasp. This was not a story of creation, but of survival. A lone survivor from a massacre of a billion, a tiny sliver of matter that somehow escaped the inferno. This is the fact that physicists at CERN have been grappling with for decades. The standard model of particle physics, our most successful theory, cannot explain why this happened. It cannot account for this minuscule preference for matter over antimatter, which is why it stands as one of the greatest unsolved mysteries of modern physics. We exist as the consequence of a mathematical imbalance that should not be there. As the universe cooled, neutrinos, which had been trapped in the dense plasma, were finally able to break free, flooding the cosmos as a faint, invisible echo. This event, which unfolded right at the end of that first second, set the stage for the annihilation that would follow. The annihilation of electrons and positrons happened later, in the lepton epoch, but the seeds of that destruction were sown in this moment. The stage was set for a universe that would be governed by matter, a universe that could build galaxies and stars and planets. Today, scientists estimate that the observable universe contains roughly 1082 atoms. Every single one of them, from the iron in your blood to the silicon in your technology, is a direct descendant of that 1 in a billion survivor. Even more staggering, NASA and Caltech researchers estimate there are around 1,089 fundamental particles, all of them born from the furious energy of that initial second. So, if the asymmetry had been zero, if annihilation had been absolute, what would have remained? A universe of fading light, a silent cosmic tomb. What if the imbalance had been slightly larger? A universe with too much matter, perhaps collapsing back in on itself before stars could even ignite. We are the improbable byproduct of a profound cosmic accident. The atmosphere you breathe, the ground beneath your feet, the chair you are sitting on, the atoms in your own eyes reading this right now, they all exist because of a lucky break in a universe that was, for a nanosecond, a furnace of annihilation. The lithium in your phone's battery, forged not in a stellar core but in the violent first minutes after the Big Bang, carries the same scars of survival. This is the point where physics stops being a set of equations and becomes a story with a protagonist. And the protagonist is the leftover. Think of it this way, and let the sheer weight of it settle into your bones. For every billion antiquarks, there was just one quark that had no partner to annihilate with. Not 1,000, not 10, but a single lonely particle. And that 1 in a billion imbalance is the only reason causality is not a philosophical exercise, the only reason entropy has something to chew on. We live in the leftover pile, the cosmic junk drawer that somehow became majestic. But the story almost ended before it began. That fleeting epoch, the lepton era, where electron and positron screamed toward each other in a final embrace of pure energy, was not silent. It was a wild blaze of annihilation, a gamma-ray fireworks display of unimaginable scale. And through this chaos, the neutrinos, those ghosts we met so briefly at the very start, slipped away. They decoupled from the frenzy, not caring about the matter-antimatter war, and became the cosmic background radiation we still detect today. They are the silent witnesses, the only particles that carry a memory of the universe before this final asymmetry was locked in. Here is the question that should stop you cold. Why was the balance tipped at all? The standard model of particle physics, our most complete map of the subatomic world, has no answer. The math works perfectly for everything else, but for this fundamental asymmetry, it offers only silence. This is not a minor footnote, this is the central, unsolved crime at the heart of existence. It is the greatest mystery in modern physics, because every other mystery only matters if matter itself exists to ask the questions. If the ratio had been different, if the asymmetry had been 10 in a billion instead of 1, the universe would be a denser, hotter place, likely collapsing back into a singularity long before galaxies could gather. If it had been 0, there would be no witnesses to mourn the emptiness. Consider the practical horror. The entire edifice of reality is built on a margin of error so thin that it is practically a rounding error itself. But here is the visceral truth that connects to your own daily struggles. This 1 in a billion survivor is your body right now. The atoms in the water you drank, the proteins in the roof of your mouth, the electrical signals firing in your brain as you process this sentence, they are all the product of an unfathomable grace period. That tiny, exhausted fraction of the universe was not merely winning the lottery, it was the lottery. It was the single grain of sand that survived a landslide, and then, through the magic of gravity and time, became a mountain range. And today, every single star in every single galaxy is burning because that one leftover particle convinced others to follow its example, to cling to being, to refuse the emptiness. We do not exist despite the destruction, we exist as the destruction. The energy released by the annihilated billions is not gone. It is still here, weaving itself into the light that leaves the sun and the warmth in your skin. You are the child of 10 billion ghosts, every one of them a potential universe that never was. Every breath is a quiet negotiation against that backdrop of total loss, a testament to the 1 in a billion chance that chaos would, for no reason at all, leave a scrap of persistence behind. Consider this fact then, not as trivia, but as a blueprint. You are the product of a cosmic near-miss. And your existence is a reminder that survival is not about strength, but about being the part that did not break. Now go sit with that silence. Can you feel the weight of being the lucky thief in the cosmic vault? You cannot observe the first second of the universe directly. At that moment, the cosmos was a dense, opaque plasma so hot that light itself couldn't travel freely, which means every photon from that era is essentially lost to us. So how can we claim to know anything about it at all? The answer is that physicists at CERN, using the Large Hadron Collider, a machine with a circumference of 27 kilometers, are doing something close to time travel by slamming lead ions together at an energy of 5.02 TeV to recreate the quark-gluon plasma that once filled all of space. It's an indirect way of studying our own beginning, but it gives us a remarkable window into a state that hasn't existed naturally for 13.8 billion years. But the particle accelerators aren't the only way we've captured the past. There's a fossil of sorts radiating through every corner of the sky called the cosmic microwave background, which is the very first light that was finally able to escape about 380,000 years after the Big Bang. Before that moment, the universe was simply too hot and too dense, and so those ancient photons hold imprints of the conditions that were set down in that very first second, even if they took hundreds of thousands of years to break free. It's like looking at a photograph of the universe as an infant, but a photograph that literally surrounds you no matter where you point a detector. The European Space Agency's Planck telescope, launched in 2009, took this measurement to nearly its physical limit by mapping those temperature variations with a precision of 1 part per million Kelvin, which was enough to confirm two huge things: that the geometry of the cosmos is perfectly flat and that the universe is 13.8 billion years old. We can even cross-check the whole story through the chemistry around us, because the nuclear reactions that took place in the first few minutes after the initial expansion settled into a very specific ratio where hydrogen makes up about 75% of ordinary matter and helium makes up about 25%, and that signature matches what we observe throughout the universe. When you see those numbers line up independently, it isn't just a guess anymore. That doesn't mean the path to knowledge has been a straight one, and a perfect example of that comes from the BICEP2 team in 2014, when they held a major press conference announcing that they had detected primordial gravitational waves, which would have been a direct confirmation of inflation happening in that first split second. It was an electrifying announcement for physicists everywhere, but within months, data from the Planck satellite showed that the signal was actually being contaminated by galactic dust, not by ripples in the fabric of space-time. It was a humbling and famous reminder that even the most confident cosmological claim demands a second look and a third one too. So when you hear someone describe what happened in the first second of the Big Bang with absolute certainty, remember that they aren't reading a written history. They're interpreting clues from a world that no longer exists. The right way to weigh a claim like that is to trace it back to the source, to ask whether it's a measurement from NASA, whether it's a result from CERN's collider, or whether it's an interpretation that's still being argued in the literature. The tools change, the theories get refined, and the evidence gets sharper, but the story is always built on the same kind of careful checks that turned a glorious mistake in 2014 into a lesson about how real science actually works. We have reached the edge of what we know, and this is where the story becomes more fascinating. The complete theory of the universe's first moment remains unfinished, according to the Stanford Encyclopedia of Philosophy, because physicists still cannot reconcile the rules of general relativity with those of quantum mechanics into a single framework they call quantum gravity. We understand how gravity bends space-time on a cosmic scale, and we understand how particles behave in the quantum world. But these two descriptions refuse to merge at the extreme conditions of the Planck time. This is the single greatest unsolved problem at the very beginning of our origin story. The struggle to bridge that gap has produced bold alternatives that challenge our most basic assumptions about the Big Bang itself. Abhay Ashtekar at Penn State has developed bounce models using loop quantum gravity, proposing that the universe may have contracted in a previous phase before bouncing outward into the one we inhabit today. A controversial idea that removes the singularity entirely. Meanwhile, researchers at the Perimeter Institute for Theoretical Physics, led by Neil Turok, have been investigating no Big Bang models, which suggest different mechanisms for the universe's expansion that avoid the starting point we have always imagined. These are not fringe theories. They are serious scientific attempts to explain data without requiring a moment where physics as we know it completely breaks down. Another path has led to the suggestion that the very fabric of reality contains more dimensions than we can perceive. String theory, as outlined in a 2014 paper on RxIV, proposes that at the Planck time, additional spatial dimensions were curled up and compacted down to a minuscule scale, around 1033 centimeters, with only our familiar 3 dimensions of space and 1 dimension of time expanding outwards. The idea is that those extra dimensions exist everywhere, but they are so tiny that we have never been able to detect them, hidden from our instruments and senses. It is a concept that moves us from a universe of simple particles to a universe composed of vibrating strings. If those extra dimensions sound strange, consider the most dizzying possibility of all, that our Big Bang was never unique. André Linde, a physicist at Stanford, extended Guth's original inflation theory in 1983 with his chaotic inflation model, and from that work has developed the idea of a multiverse. In this view, the universe is not a single finite event, but an endless expanse of inflation regions that keep spawning new Big Bangs, making our entire observable universe just one tiny bubble in an infinite ocean of other universes. Linde and many other physicists suggest that even after our universe ceased to inflate, the mechanism continues elsewhere, eternally creating new vantages of space and time. But here is the critical point. If we cannot possibly hope to test or observe those other universes, can we even call this a scientific theory, or have we crossed the line into something closer to philosophy? The questions are becoming almost too large to hold, but the data keeps arriving to keep our minds humble. The James Webb Space Telescope, which began operations in 2021, has sent back images of galaxies like those catalogued under the prefix JWST 7329, which appear to have formed only 300 to 400 million years after the Big Bang. These galaxies look far too mature for their age, with structures and shapes that should have required many more millions of years to develop, sparking an intense debate and forcing astrophysicists to re-examine their entire models of galaxy formation. Its structures should not exist so early in the universe's timeline, but they do, which means our story of the first moment still has chapters we have not yet read. So, how should you approach these grand cosmic claims with an open yet critical mind? First, never accept a single source as the definitive truth. Always check if other independent teams have replicated the findings. Second, when a new discovery seems to overturn everything we know, remember that science progresses through a long process of verification, not through the impact of a single press release. And third, accept the deep reality that our best theories are provisional, which is not a weakness of science but its greatest strength, a framework strong enough to be corrected by new information. The history of cosmology is filled with theories that once seemed absolute and were later replaced, and we must be willing to let the universe teach us what we have gotten wrong. Perhaps the most humbling thought is that all of these possibilities, from curled-up dimensions to infinite multiverses, still fall short of explaining the most immediate observation of all, the relentless arrow of time. The universe began in an almost impossibly smooth low-entropy state, and it has been moving toward increasing disorder ever since, a fact that every single physical process in your daily life confirms. Why did it start so ordered when it could have started in any configuration? What gave the initial expansion of the Planck era such a specific low-entropy character? This is not just a question about the first second. It is a question about why the past is different from the future, and why time seems to flow in only one direction for everything we can observe. So, in 1 second, the universe cooled from 100 million trillion degrees down to about 10 billion degrees, the most violent drop in temperature our cosmos has ever known. Every star you see in the night sky, every grain of sand on every beach, every cell in your body right now, all of it is dust carried over from that first breathtaking moment. The elements in your bones were forged in the hearts of stars ages later, but the fundamental particles that make them possible were locked in place before the universe was even 1 second old, when it was still a churning quantum soup, smaller than a single cell. To even glimpse that beginning is an astonishing human achievement, because we are reaching back and reading the worn pages of time itself through the words of mathematics. No one was there to take a picture, there was no camera, there was no observer at all, yet armed with the logic of physics, the scorching collisions at the Large Hadron Collider, and countless decades of theoretical work, we have reconstructed a story of creation. We built tools powerful enough to recreate the infernal conditions of the first moments of everything, and in doing so we now have a rational account of how it all began. Think about that for a moment. So what was the answer to our opening question? What actually happened in that unimaginable flash? The answer is far grander and more profound than a simple event because it is the story of your own birth. You are not just living in the universe, you are a part of it, an audience member who emerged from the opening scene of the play. You are a way for that early chaos to look back at itself and wonder, and that means every time you look up at the cosmos, you are seeing your own reflection in a history that began more than 13 billion years ago. The universe started small, but it was already writing the beginning of our story. If this journey through the first second of time has sparked your curiosity about the nature of our universe, then keep questioning, keep wondering, and keep looking up. Because this grand story of light and matter is far from over, and the next chapter, the story of how stillness turned into stars, is waiting for you. After all, who knows what other secrets are hiding in the earliest moments of everything we know?